Swayam Prabha. Digital India. Educated India.
Good morning. This is lecture number 37. It's the last session we have on module 6, matrix analysis of plane and space frames. So this is the 5th lecture in this module. This is perhaps the most difficult topic we are covering, because we are today going to deal with space frames. The space frame element is an element which has the largest number of degrees of freedom. You have 6 degrees of freedom at each of the two ends, so you have totally 12 degrees of freedom, and it's difficult, okay. But if you can really understand this, then you will find that everything else you have done till now is just a special case of this. So this is the ultimate. You are dealing with real life 3-dimensional structures, skeletal structures, and we are learning to analyze such structures when they are subject to any kind of loading, direct loading or indirect loading. So we will look at the application of stiffness methods, and really for such complex structures you need the help of a computer, because you are dealing with very large sizes of matrices, you are dealing with many simultaneous equations that need to be solved. So that is why we will use the stiffness methods, and I hope to show you both the methods, conventional stiffness method and reduced stiffness method. You will find the reduced stiffness method is also not going to be easy for a space frame, because to visualize and to write down the TD matrix is not easy. So perhaps in such an instance the conventional stiffness method is better, because you can program everything, okay. So first we look at the conventional stiffness method. So this is your element, okay. This is the element with 12 degrees of freedom. Look carefully, degrees 1 star and 7 star refer to axial degrees of freedom. That is what you had in your axial element, in your truss element, you had only that. Then which corresponds to your beam, the conventional beam, can you identify? 2 star is your conventional shear force, so you are familiar with that. 2 star is a shear force which is a moment vector 6 star, perfect, because that contributes to bending about the vertical plane. The vertical plane is the x star y star plane. So in your beam element you had 2 star 3 star as well as is it 6 star? I thought it is 8 star and 12 star, that is your conventional beam element, right. Your conventional beam element had only 2 star 6 star, 2 star is the shear force in the vertical plane, 6 star is the bending moment in the vertical plane at the start node and at the end node you had 8 star and 12 star. But you also had in the grid element you had the torsional degree of freedom, so you also had 4 star and 10 star. So it's looking familiar now, it's looking familiar now. So we've looked at the truss element, which is a special case of this space frame element. We also looked at the beam element and the grid element. If you bring in the plane frame element, then it's just a combination of the beam element and the truss element. But we have some additional degrees of freedom. What do they correspond to? What are they? Let us look at them again. 5 star is something new and 3 star is something new at the start node. what do they correspond to? That's right, shear, they correspond to shear and bending about the horizontal,
XZ plane.
in the horizontal plane, that is in the
XZ
XZ star plane. Okay, you have situations where you can have simultaneously bending in the vertical plane and the horizontal plane. Okay, if you have unsymmetrical bending, that will happen in any case. Okay, that's if your section is not symmetric, then the principal axes do not match with your global axes or with your centroidal axes. Okay, so have you, so at the end node the corresponding degrees of freedom are 10 star and 11 star and 9 star. Okay, so you are familiar with all of them. So you have 12 degrees of freedom, 6 degrees in each node. Of the 6 degrees, 1 corresponds to axial degree of freedom, 1 corresponds to the torsional degree of freedom. They are pointing along the centroidal axis, the X star axis. Then you have 2 degrees of freedom to deal with vertical plane bending and 2 degrees of freedom dealing with horizontal plane bending. The 2 would correspond to a shear and a moment. Is it clear? That is it. So you have understood physically what they mean. These are displacements and they also reflect the corresponding conjugate forces. So you have translations and rotations, and correspondingly you have forces and moments. Forces can be shear force or axial force, moment can be bending moment or twisting moment. Okay, torsional moment, twisting moment, these are words commonly used, and the rotation corresponding to that is called an angle of twist. The rotation corresponding to a bending moment is called simply rotation or flexural rotation or slope, if you wish. Okay, now that matrix is too big for us to show in one picture, so we will break it up into parts. You will know that the element stiffness matrix, which is 12 by 12, will be symmetric for sure, and that is why we can break it up into partition it into 4 6 into 6 compartments, of which you really have only Ka star and Kb star and Kc star, because the off diagonal quadrant will be the transpose of Kc star. Is it clear? Now here is your exercise. Can you write down? Can you write down? And this is the very least I expect you to do, and I could ask you this question in the examination. You do not need to solve any problem, but at least you should be able to generate from first principles with the knowledge that you already have. Can you write down for the signs convention that we are depicting here, where if you notice we defined the x star, y star, z star axes, and we aligned all the vectors in these 3 Cartesian directions, right? So what I require you to do is, let us begin with this, and let us try to understand the axes. Let us take an I section. It is a nice space frame element section to look at. So you have, if you look at it from the right side, y star is pointing upward, x star is along the longitudinal axis which goes through the center of the web out of the plane of that plane, and z star is pointing to the left if you are looking from the right. Is it clear? So with this as your reference, can you write down, and let us use these symbols, alpha to represent axial stiffness Ea by L, delta, you have 2 deltas, you have bending about the major axis, which is what we call EIZ I by Li, and bending about the weaker axis, the horizontal bending, that is EI y, it should be y by I by L, and then you have to multiply by 4 or 2, whichever is appropriate, or 6, and then you have the torsional stiffness, which is Gj by L, right. J of course has to be correctly assigned, please note, because this is a non-circular section, right. Can you write down in terms of alpha, delta, you have delta Z, delta Y and epsilon, can you write down, at least can you write down Ka star? Give it a shot. Show me that 6 by 6 matrix based on all that you have learnt till now. What is the first row, first column going to look like?
Alpha and alpha.
Alpha will, so it is going to be Ea by L, and then the rest of it will be 0. So you got the first row and the first element. What about the fourth one?
0 and last will be epsilon.
The fourth one will correspond to 4 star. So can you read off, can you tell me what that row will look like? Epsilon will come there, no? It's Gj by L. So read out that row for me, the fourth row. 0 0 0
epsilon
0
0
0 0. So you got the first row, fourth row, and you will get the columns also because it's a symmetric matrix. Now you have to worry about the second and third columns if you wish, or rows. What's the second column going to look like? 0, you begin with 0 because on the first row is 0. Then what's the diagonal element? K2 star, K2 star. Look carefully. What did you do for a beam element? What's that shear force value?
12 Vi by
12 Vi.
L square.
12 Vi by
L square.
L cubed. 12 Vi by L cubed, right? And so you got K2 2 star correctly. Which is the other non-zero element in that?
6 star.
That's right, K 6 star 2 star. What would that look like? That's a moment. Will it be positive or negative? Because if you lift up end A, you are getting a clockwise rotation, anti-clockwise moment, so be positive. So let me help you. There you are. We wrote most of it. Okay. It's not difficult, you have to learn to do this, and no looking up books for this, first principles. Is it clear? So we can write down Ka star. Next, let's move on to Kb star. Will it look like Ka star? Will there be any change between Ka star and Kb star? Look carefully and answer. Now you are shifting to the end node. You are dealing with the coordinates 7, 8, 9, 10, 11, 12. Which element? So as far as your axial stiffness is concerned, no change. Torsional stiffness, no change. Beam stiffness, what is the change if any? Shear will get reversed. Moments will not get reversed. Perfect. So I marked in green color the 6 EI by L squared value has an opposite sign to that which we assigned in Ka star. So the diagonal elements will always be positive. Yes, you had a doubt? It's correct? That's all you need to do. Okay, let's move ahead. What about the last one, Kc star? This is now off diagonal. Okay. Kc star, will it also look like Ka star? What's the difference? Huh? Where will the, okay, he's right, there will be a minus to the axial stiffness, so Ea by L will become minus Ea by L, and there will be also a minus to torsional stiffness, you will get minus Gj by L. Okay, what else? What else will change?
Shear force.
Okay, now imagine the full matrix, the full 12 by 12 matrix. Okay, if you take any column, you are actually covering all the forces in the free body, right. So you have to satisfy equilibrium. So the shears must add up to 0, then only you will have equilibrium, got it. So whatever shear forces you got in the Ka matrix will get reversed in the columns, but the moments do not get affected, because if you had chord rotation you will find the moments are going to be the same clockwise or anti-clockwise, so only those change. So here, as you rightly said, alpha and epsilon gets a negative sign, I have marked in green color, and here the shears are the diagonal elements, the shears are now the diagonal elements, okay. So you get minus 12 EI by L cubed, that is the only change, and in 5th and 6th columns the shears will be 6 EI by L squared, they get reversed. So think about it and please come prepared. Final examination you are likely to get this question of at least writing down correctly the 12 by 12 element stiffness matrix for a space frame element. Is it clear? Okay. Now you have other problems. How do you do transformations? Okay, in a plane frame the transformation was simple, you had cos theta, sin theta and 1, right, but it is not so simple in a space frame element, because you have 9 direction cosines, you have 9 direction cosines. How do you deal with this situation? So if you go to the definition, from the global axis system we want to switch to the local axis system. The global axis and local axis are not going to necessarily be oriented in the same direction. When you had a plane frame or a grid, you had rotation about some plane which did not change. Here you can have a change in all the planes. So if I have x, y, z, I can rotate it arbitrarily in any direction and I get a new x star, y star, z star. How do I do that transformation? It is a well known transformation. What is the matrix that is involved in that transformation? What is that matrix called? In linear algebra it is well known. It is a rotation matrix. We actually used a rotation matrix in the earlier transformation. So this is what it is going to look like, okay. It is an orthogonal matrix, the rotation matrix itself is an orthogonal matrix. So you have to, your transformation matrix for a 12 degree of freedom element will also be 12 by 12, it is going to have diagonal boxes, and if you get one box correctly, Ri, you have got everything. So it is quite simple, the only thing is how do you get Ri? How do you get Ri? Not so simple, not so simple. That is the first row of that R matrix. What about the other elements? Second row, third row. Okay, so let us go back to first principle. Take a look. Basically, we are trying, if you look at unit vectors, let us say, look at unit vectors, you can write down unit vectors corresponding to a global axis as x, y, z will correspond to I, j, k, right. Then I write I star, j star, k star as unit vectors corresponding to the local axes which are x star, y star, z star. I have shown an element there AB, a space frame element, whose longitudinal axis matches with x star, that is the only information you have, and you need to get these 9 direction cosines, they make up your rotation matrix. You can write them in a matrix form as Ci11, Ci12, etc., etc. So as you rightly said, the first row of that matrix is pretty easy because you have theta x, theta xx, theta xy and all that. You have, all you need is the coordinates of A and B in x, y, z in the global coordinates, then you can write it down. You just say xb minus xa by L, yb minus ya by L, zb minus za by L, you get 3 direction cosines, but they feed you only the first row in that matrix. How do you get, and you can get the length of the element automatically, how do you get the rest of it? That is the challenge. And this has to be correctly assigned because, and mistakes have been made because the I section must have its major bending axis in the direction you are going to actually do in the construction site. Let us say I have an I section, I can keep the major, I can keep it this way or I can keep it this way. It makes a big difference, and I must be sensitive to it. And in softwares, some softwares allow you extrusion, so you can actually see the final shape and you can say, oh my god, this element I oriented the wrong way, and you have got to turn it around. But you must have a foolproof way of doing it. So I think it is interesting from a vector algebra perspective, how do you do this? I have got that line x star AB and I know how it is oriented with respect to x, y, z in the global axis. How do I get the directions of y star and z star? Basically it boils down to that. Remember, let me demonstrate. I have this element, okay, and I have located it Cartesian coordinates x, y, z. So I have got x star, I have defined this perfectly with respect to the first row direction cosine. Now the y star of this is perpendicular, there are many perpendiculars I can draw. You understand, there are many perpendiculars I can draw. So how do I deal with it? So I have to, let us say this is an I section, then it defines the perpendicular because it will be in the plane of the web, right. So a line alone does not define y star and z star, I need a 3-dimensional cross section, I need a real 3D element. So how do you do it? So this problem has been, yeah, go ahead.
We can write the AB element vectorially in terms of the new coordinates, I mean the local coordinates, and we know the angle between the local coordinates and the global coordinates.
We do not know, that is a problem. We know only x star. We do not know. If we knew that, then we could have gone to that rotation matrix and filled up everything there itself. We do not know, that is the problem. It is fascinating if you look at it from a coordinate geometry perspective. So there are many ways of doing it, I will show you one simple way of doing it. A convenient way of defining the direction cosines for local y star and z star axes is by first defining a unit vector q star using some reference point q in the x star y star plane. So you have to define that plane. If it is an I section, you have to define the plane of the web. To define a plane you need one more point, and it need not be on that web, it could be anywhere in that plane. So you could pick up any other point, probably a node in the structure itself, and give those coordinates q star, so it will look like that. And then if you can write down the vector aq and normalize it, you have got a unit vector in that plane, okay. So you can do that. Get some q, get the coordinates of that, you define those coordinates, and then you can write down a unit vector q star, right. Can we do that? You can do that, and the length of the vector is known, so you can get qxi, qyi, qzi as the direction cosines of this vector. Clear? But how does this help us get the unit vectors in the y star and z star direction? What do we do next? Tell me what property to invoke, you are right. So I have got the x star unit vector which is called I star, I have got q star. With the help of these two, how do I get a perpendicular vector?
We can write any vector In terms of linear
How do I do it? Simple.
Cross product.
I take the cross product. Then I get out to get the normal to that. That's exactly what I do. I take the cross product. I know I star. I now have Q star. I take the cross product and that will point in the Z star direction, perpendicular to that yellow plane there. So I've got K star. Okay, I've got K star now, let's say. Then how do I get the J star? Perfect. That's what I do next. K star, I star, J. So simple vector mechanics, a little bit of visualization. Then if you expand these equations and solve them, you'll get these equations. And with the help of that, you've got your rotation matrix. So this, at least the theory of it, you should know. Don't worry if you don't know. Most engineers have no clue about all this because they just know how to press buttons and then the software manual tells you which button to press. Did I tell you that story about the lady who, vacuum cleaner? Was it? Did I tell you that story? Okay. It was not a vacuum cleaner, it was a mixer. Okay, so the house, the maid puts it up together and the maid is illiterate and this lady asks her, how did you manage to put it up together? And this maid says, madam, if you don't know how to read or write, you have to use your brains. So please use your brains. Okay, you've got this, then you can do the transformations. The rest of the procedure is simple, so let's straight away get into a nice juicy problem. If you can do this problem, you can do any problem. Agreed? But this is also an easy problem because I've conveniently put it all reticulated, it's all 90 degrees. So I've got another problem in the book where that element CD doesn't nicely get itself aligned along the Z axis. You have a diagonal element CO. Okay, it's solved in the book. It's solved by both conventional stiffness method and reduced element stiffness. Believe me, if you can do a problem like that with just 3 elements, you can do a problem with 200 elements. You know exactly what to do. You have a system of doing it. And that's powerful. I mean, you really have understood structural analysis. Everything else is a special case of this. So let's do this problem. So I have put all kinds of loading. I didn't throw in temperature loads and support settlement, but that's easy to do, you know what to do. Okay, so you've got 3 elements oriented in 3 completely different directions and there are distributed loads on the first one and the second one you have intermediate load and you have nodal loads at C. So you can be pretty sure that all your elements will be subject to all things possible. You will have axial forces, you will have shear forces in vertical and horizontal planes, you have bending in vertical plane, horizontal plane, you will also have a twisting moment in all of them. So this is really a great problem to solve. I don't suggest you solve it for your examination, but later in life when you have spare time, when you want to look at these nice pictures or when you like to do some programming, some coding, this is a good test case and some of your seniors have done it. Actually they validated the solution. One way to validate the solution is use a standard software package, do the same thing, you should get exactly the same solution. But we are going to do this from first principles, the coordinates are shown there and you need some more information. So very conveniently let's assume that all the members are tubular, nice tubular sections and you are given the mean radius is Ri is 150 mm and the mean thickness is 10 mm, Ti is 10 mm, E value is given to you, that's steel and Poisson's ratio nu is 0.3. With this information you should be able to crack this problem. So let's do it. So the procedure is exactly as we did earlier, we won't waste time with this. Luckily we don't have any support settlements, we don't have any indirect loading. Okay, so first we have to mark the coordinates. How many active degrees of freedom do you think we have? Active degrees. You will have active at B. How many at B you will have?
6.
Let's take a look. 6. And look how nicely we've oriented them along the global x, y, z axis, and the colors we've nicely put the green color for translations and that, what color is that, pinkish color for the rotations. Clear? You repeat this exercise at the joint C. So how many active degrees of freedom do you have? 12. How many restrained degrees of freedom you have?
12.
Again 12. So you have 6 here and 6 there. So what's the size of your overall stiffness matrix going to look like? 24 by 24. Luckily half of them are restrained. So your Ka matrix will have a size of 12 by 12. There is no way manually you are going to invert that matrix. You need the help of a computer, right? And it's a full problem because you know you can't ignore anything here. Okay. So what is the loading that is given to you? There are some nodal loads. If you notice, F7 is 30 kilonewton and F9 is 50 kilonewton, and luckily there is no support settlement. The restraint displacements are 0. Now let's write the local coordinates. Take it, this is representative of all, so I put I, but it actually matches very nicely with 2, element 2 here. We looked at this earlier. So these are local coordinates. What do you need to do next? You need to write the transformation matrix, okay? And you have 3 elements, each of them will have a size of 12 by 12, and the transformation matrix will be made up of your rotation matrix, okay? Can we write down at least the rotation matrix for element 2, which is very easy to do? What will it look like? It's an identity matrix, lucky you, right? It's an identity matrix because 2 xyz match with the global xyz, but not so for 1 and 3. So all you have to do, you can do it by inspection because in this case it's quite easy to do it, or you can get the coordinate q and play that game and solve those equations. It will be made up of 1s and 0s, but you have to put the right one at the right place, and it could be minus or plus. So I leave that exercise to you. You can generate it, and you need the linking coordinates, and they are pretty easy to remember. The linking coordinates for T1 will be, remember the start node will begin with 13, 14, 15, 16, 17, 18, and the end node will be 1 to 6. Similarly T2, the start node is 1 to 6 and the end node is 7 to 12. T3 start node is 7 to 12, end node is 19 to 20. So you are ready. Then let us go fast. T1 will look like this, okay. It is easy because you are just rotating that vector. T2 is identity matrix, is the easiest of the lot. T3 will look like this, okay. I leave it to you to figure out the rotation metric because we just do not have time for that, okay. Next you have to find the fixed end forces. You have a distributed load in element 1, that is child's play for you by now. You can find the fixed end moment and those forces. For the second element also you can find out, very easy to do, you do that. Then what do you do next? Yeah, you have to transform, you have to do the slotting game. To do that you have to put that Ti transpose, you do that. See how easy to do it with the press of a button, that is what the software does, but you have to do it correctly. You got the Ti, you do not bother to write it down on paper, let it be there, save paper, but inspect it and make sure it makes sense. And then luckily for you there is no distributed load in element 3, so you do not have to do any transformation there. Leave the linking coordinates as we have done in earlier problems. What do you do next? You have to add it all up at the right slots, and then you get your resultant force vectors FFA and FFR, okay. Then what do you do? FA minus FFA is your net load vector, and nice to draw a sketch. This is what you get. So your distributed loads have been conveniently converted to equivalent joint loads. You are now dealing with this structure, you are analyzing this structure, and the displacements you get in this structure will be exactly equal at the joints to your original loading. Okay. Then you generate the element stiffness matrices. So this story we know, you have to go through this process. You have to first get the properties. For a tubular section you can write the moments of inertia and the cross sectional area properties. You are given the Poisson's ratio in G and E, so you can write down all these values. Okay. Be consistent with your units, and then you plug in those values into your 3 elements, element 1, 2, 3, you get those numbers. If possible, write the units also and do it accurately. And then I am reproducing these. You remember these 3 pictures I discussed. That's it, you plug it all in. You get the element stiffness matrices. You have K1A, K2, K1B, K1C, K2A, K2B, K2C, K3A, K3B, K3C. Some of them may be equal because some have the same length, so you work it all out. Okay, that's it. What do you do next? What do you do next? Structure stiffness matrix. So how do you do that? Here you have to intelligently do it. We have done this earlier for the space truss or something. So you have to slot it correctly. You should know which element will go where, and once you do that you can generate the sub matrices first and then the full matrix. Personally it was a lot of fun doing this for me, I don't know for you. Okay, so now you find the displacement and support reactions, dA 12, you got the answers. Okay, effortlessly the computer has done everything, solved inverted a 12 by 12 matrix, you got the support reactions. You only wish they are all correct. The first thing you should check is equilibrium. So you do that, everything, at least they all add up to 0, right? Then what do you do next? Drawing is going to be very tough, we will draw it later. Drawing is not easy. Member forces, you do that. Like this, these are the slope deflection equations. Now you draw the free bodies. First free body. I should show you some I think I have shown some of you. I actually did this for an indoor stadium some 20 years back. All done manually, no computer. I had a 4-line programmable calculator. I entered everything. I think those days it was all basic. The code was on basic, and I had to do this in paper. I used different colors for different vectors. It was good fun. This is the first element, this is the second element. It looks nice, especially if you like colors, and you should make sure that that everything matches equilibrium set. This is your third element. Look at that. But this is not what you want. What do you really want to design? So the axial force you know, the bending moment, the shear, the twisting moment you know. The ones that are worth drawing are the bending moment diagrams. You have to draw 2 of them, one in the x star y star plane, the other in the x star z star plane. Look at that. Similarly you need shear forces. You draw in the x star y star plane, draw in the x star. If you can do all this and do it accurately, you have learnt matrix analysis of structures. This is the ultimate test. Okay, but let us do some simple problems. Let us quickly look at the reduced element stiffness method. Not recommended for big problems because it needs much more thinking. Okay, so I have done the diagonal element problem in reduced element stiffness method. You can refer to the book to do it, but let us take a very simple problem and do it. So before that, let us look at the matrix. You have a 6 degree of freedom system. Okay, so it is basically a combination of, it is your grid element plus your plane frame element with bending about the horizontal axis. Okay, first you have to put 6 constraints to make it stable, and that is how you get those vectors. Okay, it is actually eliminating 6 rows and 6 columns from your conventional stiffness matrix, you will end up with this. Okay. Incidentally, this matrix has an inverse, and the inverse you get is the flexibility matrix. So you have axial stiffness there, you have torsional stiffness there, you have flexural stiffness components there. Okay. Then this is a slide I borrowed from the plane frame, and you remember, here you have to worry about chord rotation, and that's the tricky thing, especially if you have an inclined element. If you extend it to space frame, that's what it's going to look like. You figure it out yourself later, because it takes a while to understand what gets lifted up, is it clockwise or anti-clockwise, but it can be done. It can be done systematically, you can do it. But you see, it's not so nice as this one. This is so easy. So we did a lot of problems with this in plane frames. We are not going to mess up with space frames, because if you make one mistake anywhere, you've lost everything. So do conventional stiffness method. Yeah.
The local coordinates.
Local coordinates. Okay, you need 6 local coordinates, right? Because the rank of that conventional stiffness matrix is 6. So you have to arrest 6 degrees of freedom. You have to cleverly choose those 6 degrees of freedom. Okay, then only that structure is stable, then only it can take any arbitrary load in any direction anywhere. So here what we did was we picked up whatever we learnt from the plane frame. You are familiar with the plane frame element? You are familiar with the grid element? We just had to add some more constraints for the horizontal bending. That's how it's worked out. Okay, don't break your head too much over it. A reduced element stiffness method is not recommended for space frames. Do conventional stiffness method, except when you have easy problems. So let's look at one easy problem. You can also, if you find this difficult, and I'm sure it is difficult, there's a static approach where you can get the transpose of this matrix by the contra gradient principle. You know that. Okay, let's take a simple case. Remember, we did a tripod problem, beautiful problem, which was a space truss. Now all we do is make that joint rigid, it becomes space frame. Simple problem. Just to end up on a happy note, we will do one simple problem. So it's the same old problem, except that treat the joint at O as a rigid joint, assume all the bars to have a tubular cross section. Earlier it didn't matter what cross section it had, because it was statically determinate. With a same 100 mm and thickness of 10 mm tubes, elastic modulus is given, Poisson's ratio is given, it's a steel tube. So this is what we did, space truss, and actually we solved it using a flexibility approach, because it's statically determined. Remember, all the legs are identical and the force in each leg, the vertical component is 20 kilonewton, because you have 60 kilonewton hanging from that ball and socket joint, and then you can work out the force in the actual force turns out to be 40 kilonewton compression. All the 3 legs have 40 kilonewton. What do you think will be the answer if the joint O is rigid? You will get some bending moment, you will get some shear force. Will you get some twisting moment? No, because of symmetry. You won't get twisting moment. Will you get bending moment in the perpendicular plane? You will get bending in the vertical plane, no doubt. For each of them, each element will be identical, right? So you can do a lot of tricks to simplify the problem. But my question to you is that 40 kilonewton answer that you got, will you get a different answer once you have, how much will it change?
It will not change.
Some change must be there between a rigid joint and that. Please note, it will not change if you assume axial deformations are negligible. If you assume axial deformations are negligible, you are dealing with a funicular structure. There will be no bending, no shear force. It's not possible. It's a funicular arrangement. Whether the joint is rigid or hinged makes little difference. But if you have axial deformations, this point can come down, then you can have bending, and then things can change. But in practice you will find that change is not going to be much. That is the reason why And that's the justification why even truss members you weld to one another, they are actually rigid. We model conveniently as pin jointed, because those secondary stresses you get because of the rigidity in the connection are not very significant. So let us prove that. So we are now doing a space frame solution by the reduced element stiffness method. That joint is now rigid, there is symmetry, and the solution procedure is the standard procedure, no support settlements, no indirect loading, no fixed end forces. So we will use this 6 degree of freedom element, but since we have only bending in one plane, you can reduce that element to a beam element. So that's a phenomenal simplification you could do. So such problems do by reduced element stiffness method, don't do by conventional, because you can, I mean, but you are using a an elephant instead of a hammer to drive a nail. So what do? This becomes simple. You have just EA by L and 3EI by L, because the bottom is hinged, so you take advantage of the hinge also. So it's a 2 by 2 matrix, not 12 by 12, not 6 by 6. So it's easy. You generate those matrices from first principles, you can do that. And we are looking at one of those support reactions because we want them pointing in the Y and Z directions. We are not looking at the other two because all are identical. Write down the TD matrix, write down the element stiffness matrix, generate your structure stiffness matrix. These steps are, and finally solve and find your displacement. Look at the answer you are getting. Vertical reaction will always be 20 because 3 times 20 must add up to 60, no question about that, but your axial force need not be 40. So you will find that the joint goes down by 1 mm, which is realistic, and your internal forces you can calculate, and what do you get? Instead of 40 kilonewton, you get 39.555, big deal. So you still design for 40, you are right, you will end up. And what are those moments like? Very small, negligible. That is the reason why we design trusses as trusses, even though the joints may be welded and frames. So we have finished, we have come a long way, we have finished 6 modules, the toughest module we finished today, and the next 3 sessions we will cover more from a conceptual point of view. You do not have to study for your exams except the concepts on elastic stability and second order effects. Thank you.